Hello everyone, despite the screen, I hope you can feel my sincere wishes. The topic of my presentation is BA-Audit, blockchain-based public auditing for aggregated data sharing in edge-assisted Internet of Things. This is a paper presented at SPINS 2021. The authors of this paper are Mingxi Liu et al., whom are from the following four institutions: Northeastern University, Xidian University, State Key Laboratory of Mathematical Engineering and Advanced Computing, and the strategy support Force Information Engineering University. There are some details that Associate Professor Ning is the co-first author. The Professor Wenbo is the corresponding author. And my name is Mingxi Liu. I will introduce our work in the following 5 points. Firstly is introduction. With the massive placement of sensors leading to a surge in Internet of Things data, it is wise for system administrators to use data aggregation strategies to collect and share data in edge-assisted Internet of Things scenarios, which can deplete the communication burden about uploading all this data to the cloud. Because of cloud security threats, users need to verify the integrity of aggregated data to ensure security sharing. Also, blockchain technologies can be applied to protect data security. The computational overhead and the transaction fees would be very high if our data is stored on the blockchain. Therefore, an efficient data auditing scheme is needed in this scenario. There are related works. The first is data aggregation. Fan et al. Proposed the first ciphertext data aggregation and the data security verification scheme. But this scheme has advantages that signatures cannot be verified in batches. Frequent bilinear pairs operations make high time overhead. Asma et al. Proposed a data aggregation scheme, which distribute private key to each IoT node and verify the signature according to the respective public key. But this scheme have high communication overhead. Li et al. Propose a scheme that detects the wrong aggregation results produced by the semi-honest aggregator. However, this solution cannot provide a verification mechanism when the OA tampered with the stored aggregated data. The OA means that owner application. Therefore, the existing data aggregation proposals have not supported any effective integrity verification strategy for aggregated data. The second is data auditing. Arjus et al. Proposed the proofs of retrievability scheme for the first time. The cloud can prove that the outsourcing data is stored instantly. Gatsby Attensis et al. Proposed a provable data procession scheme, which generates auditing evidence by simply reading blocks, but only a flexed data set can be audited. Wall et al. Proposed a Mocker-Hashi tree-based data integrity verification scheme. This scheme introduced an Mocker-Hashi tree, a dynamic data structure to store data signatures. Tian et al. Proposed a scheme based on dynamic Hashi tree. However, the complexity of dynamic Hashi tree retrieval is O(n), which cannot carry criminal data input. To this end, we design an index structure based on read-back tree to improve the retrieval efficiency of user application signatures during audits. We propose a blockchain-based public auditing scheme for aggregated data sharing in edge-assisted Internet of Things. We named it BA-Audit. The main work introduced the three parts. Firstly, we proposed a data sharing framework, including aggregated data auditing, where the blockchain is used as bulletin board on published data discrimination information. Secondly, we design efficient index for fast structure retrieval. The main idea is to use hash values of the aggregated data as the index symbol to construct the one-layer structure and use the dynamic adjustment strategy of the balanced binary tree to make the index structure stable. Thirdly, we design an auditing protocol to verify the data whether equal to the value before aggregating. Then let me introduce the system framework. There are 5 members in the system model. Internet of Things devices are responsible for collecting and transmitting data. Edge servers which means ES, are used for data and signature aggregation. Owner application, which is OA, can analyze the aggregation results and select some of this data for sharing. Blockchain is used for data publishing. User applications can get the data to be shared. There are 2 aspects of design goals. Functional goals contain sharing and auditing the Internet of Things data. Security goals include avoid attacks about forgery, replay, and replace. Meanwhile, the BA-Audit supports data privacy preserving. The model structure is shown as figure 1. There are 3 steps. The first is data aggregation, corresponding to the first 2 steps in phase. ES will send the collected data from Internet of Things devices at regular intervals and upload the aggregation results to the OA to analyze. The second is data sharing, which corresponds to steps 3 and 4. The OA uploads the data description information to the blockchain, and the UA can search for the required aggregated data set on the blockchain and send the data request to the OA. The last is data auditing, which corresponds to steps 5 and 6 and 7. The third section is security protocol. At first, I will introduce the index structure heft. The motivation of this work is signature retrieval is a bottleneck affecting audit time overhead. The straightforward solution is to establish a two-level index structure, retrieve the ID, yes, and then find the signature. But due to the inconstant uploading time retrieval of ES, the underlying data is not uniform. The actual retrieval complexity will be greater than OON to avoid the uneven problem caused by the secondary index. We still adopt the design of primary index. We use a hash function to connect the ESID and the timestamp, and use the hash value to construct a readback tree. The resulting retrieval time complexity is O log n. The security protocol contains 3 steps. In the data aggregation stage, we use the BGN crypto system to encrypt the data. The signature algorithm is designed by referring to the BLS signature, and the data and the signature are simultaneously aggregated. At the data sharing stage, the OA first verifies the correctness of aggregated data and then publishes data characteristics to the blockchain. The UA can use retrieval data that he wants. At the data auditing stage, the UA firstly generates a data challenge to the OA about the data what he selects. Secondly, the OA generates data proof and signature evidence and sends them to OA. Then he constructs a discriminant to verify whether the data is integrity. If passed, it sends data requests to OA. We know that Internet of Things devices generate data signatures before data aggregation. Meanwhile, the signature technology has homomorphic properties, so the UA can confirm that the data from Internet of Things to OA whether being modified. The fourth section is protocol analysis. Because of the unforgeable of signature, data errors can be detected. Because of the homomorphic encryption algorithm, ES, and the link hackers can get the data in plaintext. For experimental evaluation, we first compare the computational overhead of our heft and the Mocker hash tree from the figure 4. From the figure 3, we can know that heft has significant advantages. In figure 4, it shows a comparison of auditing time. There are 2 reasons. The first is that speech verification reduces the number of billionaire pairs. The second is that the auditing process is using heft and retrieve challenged signatures. In the conclusion section, we review our work and contributions. We propose a blockchain-based auditing scheme for aggregated data sharing called BA-Audit. For details, we firstly design blockchain-based data aggregation and sharing framework. Then we design the health index structure to achieve efficiency. Finally, we design an audit protocol to verify the integrity of aggregated data. That's all. Thank you.